Okay, I think I can start now. So I hope you are enjoying AstroCamp. I was also alumni in the third edition, I believe it was many years ago. I study math, and I'm going to talk a bit more about infinity, but in relationship to mathematics. So I'm sorry for the clickbait of the title and the image. It will not be about space or anything. I don't know if when you were kids, you did this thing that someone says, "Oh, I love you, infinity," and the other says, "I love you more than infinity." But then someone says, "Oh, there's nothing bigger than infinity." But is actually something bigger than infinity? We're gonna see that there is something that is bigger than infinity. But this is a question that has, since the beginning of the 1900s, that mathematicians knew about. For example, David Hilbert has a very famous paradox about an infinity hotel to talk about some weird properties of infinity in mathematics. So let's imagine that there is a hotel that has infinite rooms, and it's full. But what happens when a new person arrives? Well, we can just ask everyone to move uh, one door. So the door number one, the person will move to door number two, and so on. And because it's infinity, this is possible to do. And then we have a free room for this person. But what happens if there's more than one person? If there's uh, k people that arrive? Well, we do the same. We just move someone that is in door number n to door number n plus k. And now we have k rooms left. Now the thing becomes a bit tricky. Now the hotel has a line with infinite people. How can we fit everyone into this infinity hotel that is full? Well, we just need to remember that there are infinite numbers of even and odd numbers. And that's what we're going to do. So, first, we'll ask the people that are in the hotel to move to the room that is the double. So, room number one goes to room number two, room number two goes to room number four, room number three goes to room number six, and so on. And now we have infinite space for our new guests. The rooms 1, 3, 4, 7, 1, 3, 5, 7, so the odd numbers. And so the people in the line, they can go to those rooms. But now it gets even worse. What happens if we have infinite lines with infinite people? Now that seems almost impossible, but it can be done using a property of mathematics that every number has a unique prime factorization. And the reverse is true. Any prime factorization determines a number uniquely. So the first prime is the number 2. So we're going to ask the people in the hotel to move to the powers of 2. So the first person going to room 2, second to room 4, to room 8, 16, and so on. And now, for the n person in line K, we're going to move to the room 2 to the power n times 3 to the power k. Because the factorization is unique, no rooms will be repeated. But in this case, it turns out that now there's a lot of empty rooms. Actually, there are infinite empty rooms. For example, all the powers of 5, that is the next prime, are empty, and of 7, and so on. So does this mean that there is nothing bigger than infinity? No. Because in mathematics, we cannot prove that something doesn't exist just with a few examples. We just saw that for those examples, the set of people actually have the same size. But let's go a bit more now deep with some mathematical questions to have some definitions more clear. Now we just have a hotel with 12 rooms. So what does it mean that he has 12 rooms, or that there is 12 people that can go in those rooms? Or for example, what does it mean when we say that there are as many people as there are oranges in this image? So now let's go to some mathematical properties. This property of 12ness that all these three things have. So we're going to start by defining the natural numbers in a way that is not very usual. I believe that you don't talk about natural numbers this way, but this makes easy for counting. So what is the set that has no elements? Well, it's the empty set. So we're going to say, oh, 0 is going to be the empty set. Now we need a set that only has one element. Well, we have 0, so let's do a set just with 0. For a set with 2 elements, we're going to make a set with 0 and 1. So that is our number 2. And so on. The set with n plus 1 elements has all the numbers from 0 to n. And if we continue this process to infinity, we'll have the natural numbers. So this is weird because numbers defined in this way have some weird properties. For example, 0 belongs to 1. It's not like a useful property of numbers, but we're going to ignore that. And I don't know, when you learn about the natural numbers, you might have learned that 0 does not belong or that 0 belongs. It depends on the author, and sometimes it's more convenient to include 0 as part of the natural numbers, sometimes it's not. I'm going to use both during this presentation. Here, for example, it's convenient to include 0. But if you see, there's an interesting property that these numbers defined in this way are actually defined by the number before union with a set that contains it. So 1 is a set 0 union with a set just with 0. 1 is the set, 2 is the set 1 with the union a set that has only the element 1. And now we can define exactly what it means, the set of natural numbers. Because mathematically saying, oh, and then we just repeat this to infinity, it's not very precise. So the natural numbers is the smallest set that has these two properties. It contains 0, and if he has an element, then the successor is also in n. And the successor is given by this property in gray that we just saw. And what does it mean to be the smallest set? Well, it just means that if there's some set x that also satisfies the two properties, then the set of natural numbers is included in the set X. And now we can finally say what it means to have 12 rooms or 12 oranges or 12 people. We say that a set is finite if there's a number and there's a bijective function. You can also call it a one-to-one and onto function. And we call that number n the cardinality. There are two ways of writing it, either with the cardinal or with two vertical bars. I prefer the two vertical bars. That's what I'm going to use. And a set is infinite if it is not finite. And I'm not going to prove it. You can do it in the camp as an exercise if you want, that the natural numbers are actually infinite. A bit more about cardinality. If we have two sets, they have the same cardinality or they are equinumerous. If there's a bijective function between x and y. So when we say that there are as many oranges as there are people, what we are actually saying, there's some correspondence that maps every orange to a unique person. And we also say that the cardinality of x is less than that of y, or that y dominates x, if there's a injective function. So injective means that every element of x has a different element of y, but it's not guaranteed that all elements of y have a corresponding element in x. We can also talk about the other function, a function that is surjective. It's easy to see that that if x dominates y, then there's a surjective function, because it's easy from an injective function to flip the sets and make a surjective function. And now the interesting thing is, if we have two sets and we know that x dominates y and y dominates x, then it is the case that they have the same cardinality. That is, they have the same number of elements. We sort of saw that the natural numbers and the integers, they have the same cardinality already. We can do this like this. For example, 0 goes to 0, then 1 goes to 1, 2 goes to -1, 3 goes to 2, and so on. So the odd numbers are going to the positive, and the even numbers are going to the non-positive. So that's what we did in Hilbert Ortel, when there was just a single line of infinite people. So there we already saw that the natural numbers have the same cardinality of the integers. They're both infinite, but actually the infinite has the same size. And this one is also true. Might be a bit weird to think because there are even more fractions than they are natural or integers, but it is the case that they have the same amount of infinite numbers. We just need to think that a fraction is just an integer divided by a non-negative natural number. And we can do this map here. And if we continue the pattern, you can see that every number will be eventually checked out. Now you can say, oh, but this is not bijective. True. But we saw that if n dominates q and q dominates n, then they must have the same cardinality. Now, the question, what about the real numbers? Because the real numbers seems to be even bigger. Is there a way to do it for the real numbers? And the answer is yes. No, sorry. The answer is no. There is no way to do it. So the real numbers are bigger than the natural numbers. So this is strictly dominates the natural numbers. And the way we're going to prove this is by contradiction. We're going to assume that no, they have exactly the same amount of numbers. And if they have the same amount of numbers, then it would be that sorry, that is not a dominate. That would, should be an equivalence. Yeah, but if n and r have the same number of elements, then the interval from 0 to 1, including 0 and 1, must also have a bisection. And in this case, I'm going to assume that 0 is not a natural number. Let's see an example of some f. And we're going to, from here, construct a number. So for the first element, we're going to use at the first decimal place is 5. So 5 is not 0. So I'm going to put 0 on x, on the first decimal place. For the second case, 7 is not 0. So for the second decimal place of x, I'm going to put 0. For the third case, it is 0. So for the third decimal place of x, I'm going to put 1, and so on. So why are we doing this? The goal with the contradiction is to arrive at something that is not true. So we are doing this construction to see that, well, x cannot be part of this continuation. X will not be f of 5, will not be f of 6, will not be f of 100 of anything, because we are constructing it in a way that it does not match the decimal place at the position n with the value of f of n. So a bit more abstract. The decimal place I is going to be 0 if the value of f of I on the decimal place I is not 0, and will be 1 otherwise. Now we can see that there exists some natural number that f of n is x, because we assumed that f is a bijection. But if we look at the natural at position n, decimal place n, it is not the same because of the way we construct it. Because if the number is 1 or 2 or 3 or 9, then the value of xn is 0. But if the value is 0, the value of xn is 1. So if they do not match here, it means that they are not the same, which we arrive at a contradiction. And it means that the real numbers have more numbers than the natural numbers, than the integers, and then the rational numbers. Now, is there something bigger than the real numbers? If I'm asking the question, you're probably thinking, oh, there probably is. Well, there is. But we have to talk about a concept called the power set. A power set of X is just a set of all subsets. For example, if the set X only has two elements, 1 and 0, the power of X will contain the empty set, a set containing only 0, a set containing only 1, and a set containing all of it, so 0 and 1. And it turns out that the power set always strictly dominates the original set. Again, we're going to prove this by contradiction. We're going to assume that that's not the case, that they have exactly the same number of elements, and therefore there's some function that is bijective. Now we need to do a construction like we did before. We need something that will negate. So I'm going to consider the set P of all elements that do not belong to its image. We know that F is a bijection. That's the assumption. So there exists some element P that F of B equals big B. Now we have a question. Does B belong to the set or not? Well, if it does, by definition, it does not belong to F of B, but F of B is B. If it doesn't, then by definition, it belongs to F of B, which is B. Which means that we have a contradiction, and therefore the power set will strictly dominate X. So going back to our question, is there something that is bigger than the real numbers? Yes. The power set of the real numbers, and then the power set of that, and then the power set of that. So there are infinite types of infinity, and each one has more elements than before. I will just leave with a curiosity that is the power set of the natural numbers. Does he have the same elements as the real numbers? That was a question that was part of a list of 23 questions by David Hilbert in exactly the 1900. And the answer is in standard set theory, it cannot be proven one or the other. So it's up to the person to choose. That means that if we assume that there is, it will not contradict anything. If we assume that there isn't, it will also not contradict anything. So the question of the natural numbers, the power set, is the same as the real numbers? Well, it depends. And that's it for my talk about infinity. I hope it's not too bad with the mathematics. And if you have any questions,